Hello, my name is Hilary Weller. In this series of short videos we're going to be looking at advection schemes that have potential advantages over simple linear finite differences. So far in this lecture series we've found some problems with the linear finite difference schemes we've been looking at, for example forward in time, backward in space and centered in time, centered in space. Problems we've encountered. First order schemes such as forward in time, backward in space are very diffusive. The second order schemes such as centered in time, centered in space suffer from dispersion errors which contaminate the solution with grid scale oscillations. We looked at explicit schemes have time step restrictions which can make simulations expensive if you have to run with a small time step. For example, if you have high wind speed or high resolution. The grid scale oscillation problem with grid scale oscillations in the second of these problems is consistent with Godunov's theorem. Godunov's theorem states that linear numerical schemes for solving PDEs have the property of not generating new extrema, i.e. monotone schemes, only if they're first order accurate. So if you've got a second order accurate scheme and it's a linear scheme, it will generate new extrema. So we're going to look at some alternatives. Semi-Lagrangian advection, and this is to avoid time step restriction of explicit schemes. We're going to look at using artificial diffusion to remove spurious oscillations. I will introduce the finite volume method and then a few particular examples of the finite volume method, the Lax-Wendroff and warming and beam schemes, and total variation diminishing or TVD schemes. The TVD schemes are designed not to produce new extrema and they're non-linear schemes. So in the next video we'll start by looking at semi-Lagrangian.